Moore's law has been a driving force behind the rapid advancement of technology. This observation stated that the number of transistors on integrated circuits doubles approximately every 2 years, leading to a significant increase in computing power. However, as the early 2000s marked the end of what some referred to as the free ride era, developers encountered new challenges and were compelled to seek innovative and power-efficient solutions to further enhance performance. This led to the emergence of multi-core and heterogeneous systems, which incorporated a range of processing units including general-purpose processors, SIMD units, and specialized accelerators such as graphics processing units. And to exploit hardware characteristics in those new programming models have been introduced, such as OpenMP, OpenCL, CUDA, HIP, and ISPC. But when you consider those programming models which are mainly leverages parallelism, there are certain drawbacks to them. 1. Steep learning curve and lack of programmability. Unlike OpenMP, other programming models such as OpenCL, CUDA are rich with syntax and therefore have a steep learning curve, which also inhibits the programmability of those. 2. Tight coupling between program logic and scheduling details. A major limitation of those programming models is the requirement to specify platform-dependent kernel implementation details alongside the program logic. For example, NOMP threads, and thread limit in OpenMP, which is used to control kernel launch sizes, the local and global sizes in both OpenCL and CUDA. This hampers developer productivity as it necessitates considering both domain-specific and hardware-specific optimizations simultaneously. 3. Lack of portability. Existing programming models often struggled to provide consistent performance across different platforms, making it challenging for developers to create applications that run seamlessly on various hardware architectures. And with the tight coupling with the programming model and vendor-specific hardware such as CUDA and NVIDIA, HIP and AMD, ISPC and Intel, this makes more complex and harder. Another limitation is the inability to transform and tune kernels at runtime. This capability could significantly enhance performance and reduce time spent on optimizing kernels. Just-in-time compilation enables more efficient resource utilization, dynamic optimization, lower memory usage, and greater flexibility. This is where NOMP comes into play. NOMP separates optimizations from the algorithm, enabling an HPC engineer to fine-tune the optimizations while a domain expert focuses on writing the algorithm. The NOMP program contains the logic and the optimizations are within a separate Python script. By decoupling hardware-specific details from the code, NOMP ensures portability. The use of pragmas makes programming with NOMP straightforward. Furthermore, NOMP is just-in-time compiled, providing runtime availability for additional optimization details. It offers different backends, such as CUDA and HIP, to maximize performance on specific device types. Let's now see how NOMP works. At first, the domain expert writes the algorithm including NOMP pragma. This program is then passed to Clang frontend, where the NOMP pragma are replaced with NOMP runtime function calls. Then an executable is generated and is linked with the NOMP runtime libnomp. The HPC engineer can then write a Python optimization script which can be used when running the program. The optimization script contains platform-specific optimizations and is written using Loopy. The compilation of NOMP using NOMP-CC, the NOMP compiler, and the execution of the generated binary file is demonstrated here. The NOMP programming language was evaluated in 2 phases. Initially, unit kernels in the domain of scientific computing were used to assess the non-functional requirements of the NOMP compiler. Secondly, a mini application was chosen to demonstrate how NOMP can fill the research gap with its unique potential. Unit kernels such as matrix multiplication, vector addition, pi integration, prefix sum, Mandelbrot, and others are used to evaluate non-functional requirements of the compiler. The performance is assessed through 2 approaches. Firstly, native source code for the selected NOMP backend is written, and the performance of NOMP is compared against the compiled native source code. For example, the graph demonstrates performance of a unit kernel written in CUDA against the performance of NOMP with the NOMP backend specified as CUDA. Secondly, the performance of the NOMP program is compared against the roofline model to evaluate the achieved percentage of the peak resource utilization. The results demonstrated NOMP having a similar performance to native implementation. User-friendliness demonstrates the ease of writing NOMP code in comparison to writing the entire source code using the targeted specific backends such as CUDA and OpenCL. The extent of portability across multiple devices using a single codebase while preserving the performance of the application. The coverage showcases the overall percentage of scientific application types that can be implemented using NOMP. NOMP HIP performance was also tested as against the native implementations, and the results showcased similar performance to native HIP and CUDA. The GraphBLOS API serves as the selected mini application to demonstrate the usefulness of NOMP in the related context area. GraphBLOS is an API specification which provides linear algebra functions for performing graph algorithms. For example, BFS algorithm in GraphBLOS is implemented as a matrix vector multiplication between the transpose of adjacency matrix of a graph and the frontier of the BFS algorithm. When considering the existing implementation of GraphBLOS, there was a necessity of having a performant portable version of GraphBLOS. The graph algorithms BFS, PageRank and the single source shortest path was implemented using NOMP following the GraphBLOS specification. The evaluation of the mini application was conducted in two ways. In the first approach, the NOMP implementation of the GraphBLOS API was included in a performance comparison alongside alternative implementations such as Sweet Sparse and GapBS. For the dataset, the graphs in Sweet Sparse dataset was used, which provides a variety of standard datasets for evaluating graph algorithms. The results of the comparison demonstrated clear performance improvements in NOMP when compared to both Sweet Sparse and GapBS. The roofline graphs too demonstrated a comparatively high resource utilization efficiency in NOMP. Try NOMP and experience the true power of high-performance computing when efficiency meets portability.